Okay, I think we believe that we are all good. So we can start the lecture. Okay, so this lecture is on visual imitation. So in the last lecture, you learned about uh, demonstrations, learning from demonstrations, but in the style which is called behavior cloning, which is teleoperation. So essentially, you make the robot go through a series of motions under where the human is dictating all the choices. And that's a pretty popular approach today. So behavior cloning using diffusion policies. So I talked about this 2 lectures ago. Now, this is not the way a child can learn, right? Because an adult cannot control the activations of the neurons of the child's brain so as to get the child to lift up her hands in exactly the right way and so on. So that is a mode that we have used for teaching robots, but it is not parallel to anything which we have with how children acquire knowledge from adults. So today, what I'm going to do is to talk about visual imitation in the way it actually works in humans and how we can draw upon that for robots. Okay. So I need to remind you of this philosophical slide, which I've used in the beginning of the lecture as well, which is an idea which goes back to Alan Turing, 1950, which is that we can train a child, or whether we are or not we like it, a child gets trained over time and develops and becomes an intelligent human being at some point in time. And can we emulate that process for robots or for AIs? And this was Turing's proposal, that instead of trying to produce a program to simulate the adult mind, why not produce one which simulates the child's and then subject it to an appropriate course of education. Now, in this spirit, there are insights that we can get from child development. And this is a review paper from Smith and Gasser, which has some insights on how children learn and how children start out with some background knowledge. When they're born, they already have some. And then these aspects, multimodality, incremental learning, meaning training for hierarchies, physical, meaning act in the world, explore, be social, use language. So I've highlighted be social. Social here means learning from others. So this is obviously essential for language. Language is always learned from some community that you are part of. But social learning is also how we acquire skills. So if you look at modern society and, for example, industrial manufacture, okay, how do we know how to make a car, right? How do you assemble a car? I mean, these are not processes that one individual develops. These are processes which have developed over time and space. And we have a way of communicating them across generations, across peers, from parents to child, etc., etc. So this is what we are after capturing. So you have to sort of imagine that, 5 million years ago, there were these ancestors of modern humans roaming around in the savannah in Africa, and somebody developed a clever way to make a tool. And so what he or she did was to quickly communicate it to all his friends. And then, so that tribe became a little bit smarter, and so on and so forth. Okay. So how do we do? So let's try to capture this idea of visual imitation. And I'm going to do this with Anju walks in at just the right time. Okay. And this lecture is going to be in 2 parts. The first part is going to be about locomotion and navigation, and the second part is about manipulation. And in both cases, what I'm trying to do is how do we do social learning from others. And I'm going to start with this example, which is 2018. So this is now actually 6 years old. And the basic idea is the following. Okay. So think of all these tasks. Okay. All these capabilities that humans have. Various, and all of this you can find YouTube's videos on YouTube. And we want to make our robot do this. So what is that classical way that Boston Dynamics, which you have to think of as the leading company building humanoids at that time, like the Atlas was the leading humanoid in 2018. How would you train an Atlas to do these tasks? So how they would do it is they would sit down and think hard and design a controller with the MPC. Okay. Or you might say, okay, the revolutionary idea would be let's do reinforcement learning. But good luck, right? I mean, the number of trials you would need to manage to succeed to do a cartwheel is immense. So somehow we want to find a way of using all this data, and the promise here obviously is there's huge amounts of data on YouTube, and can we use this data to train your humanoid to do any of these actions? So what are we going to do? So, so there was at that time already some preceding context, which was deep reinforcement learning based motion imitation. So this deep mimic paper. Okay. So this is the world of computer graphics actually, as much as the world of robotics. So in computer graphics, they have to animate characters, right? And they have different ways of doing it. One way of doing it is that an artist draws in each frame the pose of the character. And another way, which has been going on for some time, is mocap. Mocap means that you have humans who have some sensors on their body, and then you have some setup where you have multiple cameras detecting those sensors, and then you can essentially get the sequence of joint angles over time. And you use that. So this is a way to economize on the work of the animator, makes the job of that. And they used to be 20 years ago. There used to be these debates where there were people who said, "Oh, we don't do motion capture. That's sort of in a way degrading. That's just copying human motion. We have artists who are creative and who are going to do it all themselves." So those debates are all kind of tired because everybody uses motion capture to some extent. Okay, and then okay, so we have recorded joint angles. Now we then do reinforcement learning to make this robot do all this. Okay, so just think of what do you think are the steps which are needed here, and what is that makes this problem interesting as opposed to just trivial? So you could just say we have all the motion of the human, the robot does exactly the same thing. It's because the robot's body is not the same as the human body. That's a very key issue. So this is the retargeting problem. The size and shape of the human body is different from the robot's body. Okay, if the robot is going to perform all those actions in physical space, then they have to be correct for the body of the robot. Okay, so that's problem one. So therefore, so then what use is this? So then what use is the data that you have collected in humans. So we are going to have to do reinforcement learning in a simulator. Reinforcement learning in a simulator ensures that what you're going to learn is physically plausible. I mean, at least it's plausible in simulation. Then you have to solve the sim to real problem. But the body is different. So retargeting doesn't solve the problem of it being physically consistent. So what you do is, the idea is that, and there's maybe some task like hit target. So the key insight is that, first of all, we're going to get rid of this motion capture. And of course, this is where the power of computer vision is going to come in. But that's just makes it convenient. And now you suddenly have access to huge amounts of data. But the central problem is there is retargeting needed because there are different bodies, but retargeting is not enough because you need it to be physically consistent. So what you do is you convert the human video into something for the robot to copy at every frame of time. It will not copy it exactly. So the insight is the following. So suppose if there is a child, if I'm a teacher, I'm a coach, and you're a student, and you're trying to copy what I'm doing, you're going to try to copy. If I do this, I mean, like suppose you go to a yoga class. I mean, that's a good example. You go to a yoga class and you try to copy the teacher. You will try to imitate in your body, okay? And you will not succeed, but you have a reference for every moment in time. So that's what we are trying to do. So at every moment in time, now you've got a reference pose, which is that of the human. So what's the benefit of that? In reinforcement learning, the challenge is always that of it being a sparse reward. I mean, you do a whole bunch of stuff, and at the end, either you win the chess game or you don't win the chess game. And now suddenly it's become dense reward, because at every frame you are saying, be kind of like your teacher or coach. So it is a reinforcement learning problem. There is no way to avoid the search. There is a search which is needed in terms of inaction space, which is exactly what torques to apply at every joint. You're not getting out of that. Okay, so it is a reinforcement learning problem, and the search inherent in reinforcement learning cannot be avoided. What you are benefiting from is that instead of a sparse reward at the end, you get a dense reward at every frame. At every frame, you try to copy the pose. That's it. That's the key idea. And we did this by using HMR, which is Aju's work. And let's see some examples of how well it worked. And people are there are versions of this idea. I mean, like there's a recent set of stuff out of Stanford, but which is 2024. But I think we did all this in 2018. Okay. Okay. So this is the human video, and then we convert it to we 3Dify it, and so this is the computer vision part of the problem. And then now this becomes a series of dense rewards for the robot to copy. So always when you're going to do visual imitation, a lot of information is missing. You only observe the external kinematics. You do not know the internal forces, torques, and so forth. You do not know the intentions. All of that is missing. Goals, intentions, and forces and torques. All of that are missing. So those have to be guessed. So therefore, it always has to be in the context of some physics simulator and some kind of a reinforcement learning algorithm. Okay, but now you have a policy which is physically valid, so you can put it on different environments and check for robustness. So here are just like more examples that you could do it for just not one motion, but many motions. Okay. Okay. I also want to tell you, I mean, just since behavior cloning with teleop is so popular these days, do you think that you can teach your robot to do this by behavior cloning? No, right? Okay. So I'll rest my case because this is the most popular technique these days. So, okay. And I think it didn't work on Gangnam Style, right? Andrew, if you yeah, the perception part. It would work today. I see. So it couldn't train. Yeah. Okay. Okay. So now you know. So this is gives you a demonstration of how visual imitation could work, and there are variations of this. So there are aspects of this problem which are easier. In the second lecture, I'm going to talk about manipulation. And manipulation is much harder because you have to now operate in contact with an object, and that makes life more difficult. So in here, we are dealing with movements in free space. And but for this, there's a very natural approach. Okay, so now I want to give you a little bit of background on the underlying computer vision technique. And this is a problem on which we have worked on for years, or the computer vision community has worked for decades. And I, in particular, have worked for 25 years. And finally, with this paper, we claim that we have solved this problem. Okay. So, so first, let's understand the setup. So the setup is that if you have a single frame with people, that's a 2D XY observation. Now, what we can do is to lift it to 3D, right? That's one way of doing it. So that would be XYZ. But in fact, the original data is 3D as well, but that's 3D in a different way, which is X, Y, and time, because you have a video. Okay. So if you put these two ideas together, that you lift every person to 3D and they are moving in time, then what does that correspond to? That's 4D. So what our goal is that we have humans moving around in space and time, and we infer the true state. So the true state is this 4-dimensional thing. Okay, so how do we do it? So this is the paper from last year. I have to give you some more background as to the techniques for this. So the techniques go back to this earlier paper from 2018, which is HMR 1.0. And the key thing here is that we have to have a model for the person. So how do we think about the person? So normally, computer vision people like dealing with rigid objects. So a whole lot of the theory of structure from motion is based on rigid objects seen from multiple cameras. Humans are distinctly non-rigid. We have all these body parts, and the joints are going to be various angles and so on. So a priori, this problem feels totally hopeless. Like, how are we going to solve this problem? Because a structure from motion is hard enough from reconstructing from multiple views. Here you have maybe only a single view, and the object is non-rigid. Okay, so what is going to save you? What's going to save you is essentially top-down knowledge. Top-down knowledge of the structure of the human body. So let us, for the moment, assume that all of us are identically shaped. So you have exactly, so if you have 1 unit of size for your head, then the full body is 8 units or 7.5 units. There is this old picture of the Vitruvian man that Leonardo popularized, where the artists know this, right? So the different portions of the body have a certain ratio to each other. It's slightly different for men and women. It's slightly different for kids versus adults, but we're going to hand wave about this a little bit. Okay. So what we have then is if you just consider the skeleton, we have a certain number of degrees of freedom, which are all the joint angles. Okay, so that we are going to capture in this term pose. So pose is all the joint angles. Shape here is going to deal with essentially, are you thin? Are you plump? Are you tall? Are you, a child, male, female? So those variations are dealt with in this shape space. And essentially, the way you construct this shape space is that you have measurements on lots of humans, and then you do some kind of a principal component analysis. Okay. And then, of course, you have this viewed by a camera. And let's say we used a scaled orthography assumption. So there's a rotation and translation of the camera with respect to the human. And then the scaling factor essentially captures how far away the person is with respect to the camera. Okay. So so we have now reduced the number of degrees of freedom. It's become a finite problem because it's all of these are a small set of numbers, like 50 numbers or 70 numbers or whatever. And now, what is the signal for this? So the signal for this is going to be if how do I do the reconstruction? In 2D, I can find the key points. So in 2D, I can locate the left elbow, left shoulder, right shoulder, etc. And what we know is that the 3D positions of the joint should be such that when you project them in the image, they should be consistent with the 2D projections. So this is what's called reprojection loss. This is a standard term in computer vision, so popularized from the structure from motion work. Structure from motion, SLAM, all of this is about finding a 3D positions of points such that the reprojection error is minimized. Okay. So that's indicated by this. So you have a 3D model, you project it in the image, and then the 2D key points have to line up. Okay. Okay, you do this in a straightforward way, and you get these horrible reconstructions. So these reconstructions are monsters of some sort. But what is true about these monsters is that if you look at just the projections of those key points, they are actually correct. So the 3D key points of these monsters, when projected to the image, are accurate. They lie in the right 2D key points. So what has happened is that you walked off the manifold. There's a manifold of what valid human shapes are, and you walked off from it. So what do we need to do? Okay, so this is again, these are techniques from that time. So there's deja vu here. At that time, if you want to check that is it consistent, the way you would do this is to use some kind of a GAN. So a GAN would say, there would be a discriminator which would say, are you off the human manifold or are you not? And you should be on the human manifold. So, okay, so there you have the discriminator, and that's going to check whether you are on the manifold of human shapes. And how do you train that? So for this, you need genuine 3D data, but you need only a small amount of it so that you are capturing the shapes of true humans. And the reprojection error, that constraint can be exploited on general images, right? Because you want those because those will capture humans in a variety of poses, with occlusion, with objects, etc., etc. So, and you can get millions of images, and for this, the machinery is modern computer vision knows what to do with. You hire a bunch of people, they sit somewhere, and you click points, left elbow, left shoulder, right shoulder. And okay, it's painful, but if you're a big company, you have a budget for such things. And once you've collected a million images, you have the training data. So computer vision today, the big successes of computer vision are really all successes, not a big data. Maybe it is a success of big data, but it's really a big supervision. Okay. Okay. So okay. Blah, blah, blah. Okay. So then what do we do? More recently, we essentially just took it to scale. You have a lot more data. You have a more powerful model. You have used a transformer, of course, now, and then you work hard, and then okay. So that's one part of the story. The second part of the story, which actually is very, very important, is that in the real world, if you want to do 4D reconstructions, you are going to have to deal with images or video with many people. So therefore, you have to solve the tracking problem. Okay, the tracking problem has existed from the early days of computer vision. It really goes back actually to before computer vision in radar and so on. So radar was invented around World War II and used very successfully in World War II. So you have enemy aircraft coming in, you want to detect them, you want to track them, and then you want to have your strategy. Okay, so then there were versions of this for images and video and so on. Now, we want to, if you have some video with many people, you want to track each person, and you want to know the identity that, okay, person A matches to A prime in the next frame, and so on. So again, huge literature, but the important insight here is that if you do this with 3D features, it's going to be much better. And what are the 3D features we can think of? So we can think of appearance, we can think of pose, we can think of location. Okay, so let me maybe show this idea why we want to do tracking in 3D rather than in 2D. So let's see if this demo. Okay. Okay, so in 2D, this is what happens, right? When objects move, they can occlude each other from the perspective of a camera. But what happens in 3D? In the 3D, nobody is ever occluded. They always exist. So my slogan for this is normally out of sight is out of mind. When somebody disappears behind a tree, they are out of sight. But in 3D, all the identities are always there. Out of sight is not out of mind. People are always there in this three-dimensional world. So if your representation is a three-dimensional representation, then these people never disappear. They're always there. They only disappear in a 2D projection. In the 3D world, nothing bad has happened to them. Okay, that's one insight. Second insight is how tracking works is essentially that you're going to do some kind of matching of features. And matching of features traditionally meant matching of pixel values. So consider this one guy this is, I think, some rugby player, and you have four different poses of this fellow. Okay. If you look at it and let's look at the neighborhood of his right shoulder that's indicated by that target point. If you think of it in 2D, in pixel space, the appearance is changing a lot, right? If you think of it in 3D, okay, so we're looking at that point, and in 3D, how do I think about it? In 3D, the way I should think about it is that there is a texture map on his body, which corresponds to like the color of his skin, the color of his clothes, etc., etc. So there is a on the mesh of the body here. What's the color? It's like the color of my sweater. And what's the color here? It's the color of my skin, and so on. And that, as I move around, doesn't change. Whereas the 2D appearance is changing constantly. So therefore, you need to do that. So you need to have. So anyway, let me go back to that slide, which now gives the tracking algorithm. So the tracking algorithm essentially says we recover the 3D pose, we recover the 3D locations of the key points, we recover the appearance, which is going to be a texture map on the body of the person. And now, now you project from time t to t plus 1. So the movement of the person, okay, you just use a local linear approximation. Pose, you can have a learned model on how the pose changes. And the appearance, you just model as constant. Because I'm not changing my clothing every 1/30th of a second. And that's it. So by just going to 3D, we have made the problem easier, but it requires the tracking problem becomes easier, but it requires doing the lifting to 3D. And here I'm going to make a meta remark. A lot of robotics will benefit from using 3D computer vision rather than 2D computer vision. And this is like a general remark, which I think will play out in the next few years. So many of these robotics tasks where they're using 2D images, if they use 3D information, they would just be much more natural. There would be invariances built in and so on. But that's a small editorial remark. Anyway, so this is meant to show that the tracking works. And then this is the proof of the pudding, which is that we can do reconstructions. So up in the top left, you see the raw video, and in the bottom, you see the reconstruction. Now, what is noteworthy here is everybody can do 3D reconstructions. The question is, can you really do 3D reconstruction? And the test is, does the technique work when there are many people occluding each other? Does your technique work when the poses are unusual? Okay. Because just straightforward standing person, anybody can do that. So the test was unusual poses and dealing with crowding because of multiple people, objects, etc. So this is what we can do. So here the reconstruction is frame by frame. So this is the unusual pose. So there are people who claim that they have good reconstruction algorithms. The test is whether they'll work on video of this type. And I mean, I could go on forever, but I think I want to show the next dance sequence because I've had people work on this for 25 years. So this is being done frame by frame. So this is the test that you don't get confused by multiple people and so on. Okay. I think I'll stop here. Okay. Okay, so what are the next steps? So in fact, the paper SFV was based on the previous version of HMR. So I think now we have better technology. And the half-life of any computer vision state-of-the-art model is about 6 months. So normally in 6 months, whatever you claim is state-of-the-art gets beaten by somebody. This paper, I think we are at what, 1.5 years? What is it, Anju? Yeah. But I mean, we had done it, of course, before that, right? We submitted. So as of yet, it is still state of the art. Okay. So which by our community standards is a record. Okay. Okay. What are the next steps? Okay. So now let me see what we can do with this. Yeah.
Like set of methods would benefit from like being learned on video or like have some sort of like temporal
The answer is yes, of course. But the point here is to show what you can do with a single frame, because sometimes you have to process just a single frame. So temporal smoothing can always, I mean, always whenever you have a more sophisticated model, it should do better for you. I mean, yeah, and it opens up a whole lot of other problems, like not problems, but actually opportunities like prediction and so on. But I'm not going to get into that here right now. So first, I want to show that this idea of learning from video is not just in simulation. So that work was just in simulation, but it's like 2018. So the more recent work is that we can actually use this for training real humanoids. And this is work led by Ilya. And so here is a robot walking around in San Francisco. So this is the Digit robot, which is it's a headless humanoid. It has no vision, it's blind. Okay. And then, oh yeah, let's have this video too. So, I mean, all these walking robot people, they have to show that it walks in different terrains. And then if you poke at it with a stick, it doesn't fall. So these are the kinds of demos that you need to see. And okay, so what's the machinery? So this is now proof that this is a real robot working in the real world. And I won't get into the details here, but this is a transformer-based policy. And it's been trained with a whole lot of trajectories, and the trajectories are derived from multiple sources. So the trajectories could come from a previously trained neural network policy trained with reinforcement learning, could come from MPC-based controller that the manufacturer supplies. It could come from motion capture, mocap data, or from internet videos. So these are just examples of the different sources of data. But so this is like an example of the data from humans. So this is so we have like this video of this person walking, and now you use that for training this robot. Let's see if that's shown here. So what problem do we have to solve first here? This is going to generate a fake trajectory basically, where you've copied the human movement into the robot's movement. So you have to solve the retargeting problem. So retargeting always involves in some kind of correspondence and imposing some constraints. And this is a problem that has to be dealt with for full body robots, like humanoids, and it has to be dealt with for the hand case, because the human hand is not going to be identical to the robot hand. So the retargeting problem is always with you, and people typically solve it by some kind of human intervention. So the human identifies correspondences of fingers or joints or what have you. Okay. And then the other aspect is that the training procedure. So the training procedure has to deal with incomplete data. So I already alluded to that in the SFE work, that you do not know information about forces and torques and so on. You do not know the goals and intentions. So goals and intentions get translated to actions. So what did the human actually want to do? What joint angle did the human's motor cortex and cerebellum command? And then what did the joints deliver? There's a gap between what you want, which is determined by your brain, and what is actually delivered, which is the musculoskeletal system. So all of that is a problem. So in the previous SFE example, that was being dealt with by reinforcement learning, that you just made it into a dense reward situation. Here, the machinery is different. So the machinery here is next token prediction, but with missing data. So some tokens are missing, and you have to try to deal with that. And that's what is the trick here. Okay. So I think the future is actually quite bright, because for these whole body motion of humanoids, and I could have brought more contemporary papers. I think I would cite work from, say, Xiaolong Wang's group at UCSD, where they have done various kinds of imitation for robots dancing and so on. So I think the role of imitation learning for humanoids is here to stay. I think the basic methodology works. I want to now turn to something more abstract, and which is to say that we can learn from human videos at many levels of abstraction. And there's this beautiful slide I got from Saurabh Gupta, which I agree with fully. So therefore, I thought I would steal his slide rather than make it myself. Okay. So there's a lowest level of where you can compare robots and humans, which is muscle tensions in the human and torques in the motors. Okay. Then there are macro actions, right? Like take one step forward. Then macro actions might be joint angle changes. Skills might be walking, running, picking up, tearing something, throwing, so on. Then goals and sub-goals and goals. So what you have is, when you see a video of a human or humans performing actions, in some sense, you have some signal for all of these. And you can try to avail of that for robots at any of these levels, right? So these are just levels of abstraction, because all human behavior is hierarchical. So robot behavior is also hierarchical. and you can use information at any of these levels. So what should I do? Let me move this stupid thing out. So depending on, so we can use, so there is an embodiment gap, right? The body of the robot is not the same as the body of the human, but it may not, it doesn't matter with respect to goals, right? So the more you can essentially get the benefit of visual imitation at different levels of this hierarchy. And when you do it at a more abstracted level, the body of the robot is no longer so much of a problem. Okay. And then I want to show you examples of a paper we did. Okay, so there's the lower level of the skill. Okay. Okay, so this is actually a paper from our lab from 2019. Okay, and so this is, we have, let's say, a video of humans walking around in some environment, right? Okay, and I want to learn from this for a robot walking around. Okay, and the robot in this case was a wheeled robot, and the human obviously is walking around. So the low level, joint angle command for the human legs, translating that into robot wheel commands is silly, right? It doesn't make sense. So you don't want to be doing the transfer at the lower level. So what can you do here? But you can do a transfer at a mid-level and a higher level. Because when you walk around, what are the insights that you have here? When you look at this, look at that picture at the bottom. What is that? And now you'll see the next steps of the human walking through it. It'll basically tell you that this is open space through which you can go. There's a door to which you can go. This is the concept of an affordance, going back to Gibson. So affordance is how you can interact with an object or some aspect of the environment. So essentially, what is being revealed here is the affordance of a door, which when a human is walking through that space, you have that. Okay. Okay, then you also acquire essentially subroutines or operators or when we walk, what do? We tend to do, like when I walk out of that door into this classroom, what am I going to do? Very likely I'm going to turn right. When we come out of a door, we often turn left or we turn right. This is a stereotype behavior. And if you have lots of videos of humans navigating around in a space with egocentric cameras, you will have that in the data. So essentially what I'm saying is that you can operate at one higher level of abstraction. Not the level of abstraction which is take one step forward or one step to the left or one step to the right. You can operate at the level of go a few steps in the direction in which you're heading, or turn to the right or turn to the left. So there's a nice coupling here, because the affordance is what can you do, and the subroutine is how, what do you do? Okay. And we can learn this. So if you turn left, you get this story, you turn right. So this is what we had was that the robot learned these subroutines. And so let's say what we did. So there's a robot interacting with an environment, and we want this robot interacting with an environment, and then we have first-person videos from walking people. Okay, so how do we make use of this? And we are going to, this machinery at the end is going to give us two things. One is an affordance model, which in this case translates to what subroutine to use where. Okay. Affordance models are going to play a major role with object manipulation. Okay, and if you think that this is a trivial problem, I commend to you the problem that you face when you go to a new hotel in a new country and you cannot figure out how to get the hot and cold to work properly. I mean, because every country I go to and every hotel I go to, they have a different way of sort of how to get the hot and cold water, and you have to figure out the affordances of this particular shower system before you manage to get scalded, right? Or when you approach a door, I mean, canonical example, some knobs have to be turned to the right, some knobs have to be turned to the left. Some cases, it's like knob that you have to push. Some cases, it has to be pulled. So we as adults have trouble with this. So just imagine a 2-year-old child, right? I mean, so affordances are a thing. In the world we live in, there is a process by which we acquire this specialist knowledge of how to operate on an object or interact with an environment. Yeah.
Like hard-coded or?
No, they all emerge with learning. Yeah.
Oh, so when your affordance model like chooses which subroutine to use, do you have like a cap of how many subroutines like you know?
It's like 5 or 10 or something. Yeah. I mean, I'm not going to go. I'll have 1 or 2 slides with the gory details. The details. This is 2019. We can do this much more fancy now with all the tools we have today. But the core ideas of this, I actually was just reminded of it because I was preparing this lecture, are pretty good, even if I say so myself. Okay. Okay, so what are the details? Okay, yeah, so the details are the video. And then we did one more trick, which is that a video will be a series of images, and you want to figure out the action. What is the action associated with this? So it turns out that you can do this with a little bit of interaction data. And this is itself a good principle. When a child learns, most of what the child may learn may be through observation. But observation is passive. You are not performing the action, someone else is performing the action. And then there is interaction, which is different from observation. Interaction is, I do stuff in my body. So when I pick up this object, it's in my body, right? As opposed to you picking up this bottle. And I get more information when I pick up the bottle. The difference is my own life is going to be like 10,000 hours, and the life of others is 156 million hours on YouTube. So you need to find a judicious way of using a small amount of interaction data and a lot more observation data. Okay. So here, this is the observation of a video, but what we can do is we can actually, if a robot actually moves through an environment, then the robot knows its own commands. So you can essentially get a label of the actions. So you can then say, given these 2 images, can I predict what was the action that I took, right? So I can pseudo label this, and this is not a surprise, because if you think of it from a computer vision perspective, you are moving through a space, so structure from motion will tell you what is the movement that you did for the change of image. But you can actually learn it do it in a learning style as well. Okay, so you essentially can do so you, with the help of this little model that you train on interaction data, now you can take all this video and you can pseudo label it with the actions that were going on in this person. And the actions are, in this case, go straight, turn left, turn right. Okay. Okay, and now you throw some learning mumbo jumbo on top, which is that you're going to learn simultaneously these set of subroutines, which is like a small number of subroutines. And then you're going to learn an affordance model, which tells you what is applicable where. Yeah. And that's what we did. Okay, I'm not going to go into the details. So this is all 20, but these are the subroutines which are discovered. So let's see what the video says. So this is. So this subroutine is basically one subroutine discovers turning right, one discovers turning left, one discovers going straight, and so on. And then now you can do hierarchical RL, right? So suppose you have a goal like go to some point which is 47 meters northwest, for example. Now, so you have the usual navigation tasks. You go to some geometric goal, you go to find some television or whatever. But all of those you can operate at the lowest level if you're doing RL, or you can operate with these more abstracted approaches. And it turns out, I mean, the obligatory in all of these things, you always have some picture where there is some RL training curve, and with whatever was your clever idea, the curve should be rising higher and quicker. And sure enough, we have something like that. Okay. But again, I think the technology of this is 2018, 2019, but the key ideas actually should transfer to manipulation, which is acquiring an affordance model and acquiring subroutines. Acquiring subroutines, by the way, is to me a major interesting and scientific challenge in robotics, because I think that the future is not in end-to-end training for every skill. That is not a scalable solution. You need to have hierarchies. And the benefit of hierarchies is that you can get reusable skills, right? This walking straight is beneficial if my goal is to go to the airport, and it's also beneficial if my goal is to go to the water fountain. I can use this subroutine. Whereas if I did end-to-end training for each of these tasks, it would not help us. Finally, I cannot resist to make a dig on language, which is this is visual imitation. So now we humans always can communicate. How does a parent teach a child? So the parent can teach a child. They do use language. I'm not denying that, but there are certain abilities which are much better done by visual example than by words. And if you don't believe me, read this set of instructions on how to climb a staircase. Okay, while I drink my water. You should check it out. It's true. It's from this Julio Cortázar. So you can do all this, or you can just stand still. More or less, when you want to explain an action, you do it by visual example. You don't convert it to this hundreds of words. Okay, so now let's take a 5-minute break. I was very leisurely, so I think you do not need a 10-minute break. Just a 5-minute break will do. Okay, so we can start. Okay, so this half of the lecture is going to be, or this is lecture 8B, is going to be about visual imitation, but in the context of manipulation. And this is a harder problem than locomotion and navigation. Okay. Okay, so let me again start with a Berkeley-centric account of this. So this is a picture which shows what we might want to do. So imagine that you have this scene. So this is like somebody doing some stuff in a kitchen, and what you want to do is reconstruct the hand in 3D, reconstruct the object in 3D, and this is a paper from like 4 years ago now, which showed how to do this. This is a hard problem, and this is not a solved problem. So while I consider reconstructing the whole body to be more or less a solved problem, reconstructing the hand, and in particular the object, is not quite a solved problem. I mean, we have made progress, but there is some more years of work left on this problem. And I think that this will be very impactful, because currently a lot of the techniques that are being used by people, they are basically 2D techniques. And 2D techniques make sense if the 3Dification doesn't work. But once the 3Dification works, then I think that often working in 3D is going to turn out to be the right thing to do. But let's see what we can do today. Okay, so there's the part of reconstructing the hand in 3D, and there's a part of reconstructing the object in 3D. So the part of reconstructing the hand in 3D I think we have a lot of progress now. And this is a paper from earlier this year, which was presented at CBPR. And let me show you the results again with a video. So again, what is it that we are looking for in order to be impressed or not be impressed? Uh, there should be a wide variety of poses that you can deal with. There should be the fact that if the hand is partially occluded or if the hand is manipulating an object, then the reconstruction should still work. And here we are just looking at the reconstruction of the hand, not the object. And I'll come to that in a second. We move this along a bit. So it's again a frame by frame. So here you see object interaction. So when you see flicker, that's an indication that isolation is uncertain because maybe frames are being reconstructed slightly differently. So this gives you some sense of the noise in the reconstruction. Okay. Okay. So this is what we can do with hands. I think there is room here to do some more work. It's not, I don't think this problem is fully solved. There will be room to do a bit better, I think. But first, the numbers which show that this works well, I find this boring, but you have to show this. Okay. Okay. Oh yeah, this is like a standard kind of slide which is you find always in computer vision papers. What do you need? Somebody would say, oh, do you need big data or do you need a big model? And the answer is both. And it's been the same answer always for some years. So that's a slide which shows that if you just had more data, then the performance would be so much. If you had just a bigger model, the performance would be so much. You need more data, more bigger model, and various. Okay. Okay. So now what I want to show is what can we do for objects. So the hand reconstruction problem, we have made substantial progress, but we are maybe at the 80% point, not 100%. Okay, now there is the object reconstruction problem where maybe we are at the 50% point. Okay, so we have a lot more to do. So what can we do today? Okay, so that's what we'll show you. So what you are trying to do is to reconstruct the object in the hand. Okay, and this is a very hard problem. Why is it hard? Because you only see a few pixels on that object. And if you try to do reconstruction with structure from motion, there's not going to be enough of a variation in terms of parallax or disparity to do the reconstruction. The best way to do the reconstruction is to use top-down knowledge, familiarity with the category of the object to try to do a reconstruction. And so we built on this model called MCC, which was presented last year at CVPR. So this is essentially a generic 3Dification model, which is that you're given an image and you have some object in it, and that object is being lifted to 3D from a single image. And this works okay for certain classes of objects and scenes, but it's like the way it's not like solve the problem fully. It's not the setting that you can say, oh, this is done. We are done with this. But the belief is that over time, techniques like this will get better. So in particular, what we wanted to do was to adapt this machinery of doing 3Dification from a single image to the case of an object in the hand. An object in the hand actually offers some nice features, because first we can reconstruct the hand. So the hand is in 3D now. And now you are reconstructing the object in the context of the hand. So that defines a scale, because the object because human hands are always about the same size. So that gives you a notion of scale, like the distance between my thumb and my forefinger is like 6 centimeters or something, right? And you can guess that just from the pose. So if I'm holding this object, you get a sense of the size of this object because of the fact that my thumb and forefinger are in a certain configuration. So the objects that humans are manipulating, we get a sense of their size and shape from the fact that they are in juxtaposition with the human hand. Okay, and then additionally, what you can do is from your reconstruction, which in this case is like a point cloud, you can retrieve nearby models of objects, and then that does a denoising in some ways. So again, the usual thing where we say that our approach is better than other people's approach, and which is fine. But again, I view this as a problem on which we have made substantial progress, but there is still more room to go. But this will happen. In 6 months from now, 1 year from now, 2 years from now, computer vision will deliver on this problem. Computer vision will give you good 3D hands, it'll give you good 3D objects. It's up to the roboticists to find a way to exploit this. Because currently, the work in robotics essentially relies not on assuming that this kind of a reconstruction is possible. Okay, so just to show what some examples of successes. So here we have objects in the hand, and the different views are meant to show that that the reconstruction is actually in 3D. Okay. So, so I'm going to stop this here. And again, now by analogy with my previous talk, where I was talking about the whole body. Now imagine, so now let's indulge in wishful thinking. So let's imagine that this 3Dification process becomes really good. And now we can avail of the 156 million hours of video on YouTube, or Ego 4D, or many of these other data sets which show humans interacting with objects. So that's, okay, this is wishful thinking. It's not there yet, but but in research, you have to plan your research agenda, assuming things which are coming down the pipe. But so that's, so what will be the problems we'll have to deal with? I mean, just analogy to the previous talk, where if you wanted to have, you have humans walking, and now you want to have the Atlas robot, or the human doing a cartwheel, and you want the Atlas robot cartwheel. So you have to solve the retargeting problem. And the way you solve the so you have to solve the retargeting problem, plus you have to deal with the physical dynamics. So the way you deal with that is through reinforcement learning in a physics simulator. So one obvious remark here is that there is an analog here. So the analog here is you take human movements and now the human hand movements, and then you put them on a robot hand. So you solve the retargeting problem. And if you do it in a physics simulator, you can deal with trying to solve the deal with the physics part, the inverse dynamics. Okay, that's one line of work, and there's been a lot of work in that. Actually, more work which is of the type which is that we don't just download videos from YouTube. Rather, you have the human manipulate an object in the lab, and now you collect data which is in the right setting, and you use that for retargeting. So there's been a lot of work like that. The amount of work which is really using vanilla videos downloaded from YouTube is actually quite limited. But again, this to me is a function of the technology. As the technology gets better, we'll find more use for it. Okay, so that's at the lowest level of the hierarchy, where you're trying to convert the movements of the human hand into movements of the robot hand, ideally a multi-fingered hand. But as in the last lecture, there should be ways of using these videos for information at higher levels of abstraction. And what was it last time? It was affordances and subroutines. So there should be a counterpart to that here. So let's look at that. So again, this slide is from Saurabh Gupta. So there is a low level, in fact, mid-level, you can say subroutines and affordances. So we talked about that for navigation, but that should apply here. And then there should be even higher level stuff, which is okay, which is common sense about objects and scenes. So so this video, right? So what do we learn from this video? Actually, we learn a lot of things here. You have this video of a person opening a cabinet. What have you learned? Let's think of what kinds of things have we learned. So let me convert this to a interactive session. You watch a little clip of a human opening a cabinet. What have you learned which could be useful for a robot? So the first, yeah. Okay, good. So that's one. So there is common sense knowledge about the cabinet. Okay, that's good. Let's start from the beginning of the video clip. So the first part, what happened was that the hand approached the cabinet, and then what do you learn? You learn how to open the cabinet. So how to open the cabinet, in this case, you are not turning something. You held the handle and you pulled it towards you. So this is the affordance of the handle of the cabinet door. So you learned the affordance of that. Okay, if you think in terms of subroutines, what did you learn? You learned how to grasp that object. how to grasp that handle. So the human has a certain grasp of the handle, and then you move your arm. So you learn that. And then you learn this common sense knowledge about what are the objects contained inside a cabinet. So there's a lot of knowledge in this little video clip, which is common sense knowledge and motor control knowledge that we can get. I mean, the small detail is we don't know how to squeeze it out, but there is a lot of learning which one can do from this video, which we do not yet know how to do. So this is like the grasp, and then you open, and okay. So I'm now going to take you through a few representative papers which show what's being done these days in computer vision and in robotics. A lot of these papers are some are in the computer vision community. When you at the end you don't get a robot to do something, you publish it in CVPR. If you get the robot to do something, then you submit it to a robotics conference. So, but I think both are needed at this stage. I think this is totally okay. So what is the insight here? What sites can we interact at? And then how to interact with those sites. So A and B is basically about the affordance, and then you're also acquiring a trajectory. So this is a paper from Saurabh Gupta's group at UIUC. So I got his slides. So we learn through observation of human hands interacting with the world. Okay, so this is just more slides which go through this idea. Okay, attending to hands localizes and stabilizes active objects. Hands show where we can interact in the scene. Analyzing hands reveals information about objects, their state, and how to interact with them. So one line of work, which is sort of the obvious one, which I think we have papers going back like 5-6 years, is essentially the hotspot, what I call hotspots line of work. Hotspots is essentially where do you interact with the object. So when I look at, so here's this bottle. If you see pictures of people with bottles, I mean, this will be a very typical interaction. I do not go around with my finger, the bottle resting on my finger. So people essentially, what are the interactions with this bottle? There's this one, and and there is this one, right? So I unscrewed the top, and there's an affordance of the cap, and then there is how you carry, and then how you drink from it. And all of these you will observe in videos of people interacting with water bottles. So a robot, or a Martian who comes to Earth and wants to observe human behavior can do that by just observing humans, right?
Not similar water, for example, for cola, right? Because if you drink cola, you cannot, because of the gas, you cannot drink it like
Yeah, so the affordances are different because the content is different, right? So therefore, this is why I think manipulation is harder than locomotion and navigation. The range of affordances we have to deal with is much greater. Okay, let's see. We have lots and lots of data sets that the computer vision community has collected, which contain humans with hands interacting with objects. So a very important line of work is that from David Fui's group, which is on called 100 Days of Hands, which is understanding human hands in contact at internet scales. Okay, so you can just find lots and lots of pictures like this. Okay, so this is called a prismatic grasp. Okay, and there has been work on trying to use this for self-supervised learning, but I'm not going to go into that. Okay, this is an example of this hotspot kind of work. So the hotspot kind of work is where do we touch the object? Okay, and so that's indicated here. So like you don't touch the entire cabinet door. You typically touch it at the handle. Okay, you can also learn how you interact with objects. So this is the kind of grasp that you have for different objects, right? So this is in the grasping community, they call this functional grasping, as opposed to I mean the previous style of grasping research, which was all about how to stabilize an object. So force closure grasps are about how to pick up an object such that it doesn't fall down. Here, the way you pick up a mug, I mean, there are at least three different functional grasps I can think of. When I have a coffee mug and I want to drink from it, I lift it up from the handle. If the mug is dirty and I want to put it in the sink and I wash it, I have a different way in which I carry the mug. If I want to put the mug into the dishwasher, I will insert it in a certain way. When I want to take a clean mug out from a dishwasher and put it on my shelf, I will interact with in a different way. So your classic robotic solution of a force closure grasp is kind of meaningless. Or another example, you're sitting in a restaurant and then the waiter brings you your glass of wine. And if he brings it with a force closure grasp, you will send him away. You don't want the person's dirty fingers on your wine, right? So grasping is really ultimately, in that sense, it becomes a learning problem. Okay, because we observe how humans interact with objects. It's not just that. I mean, there is obviously a part to do with the physics, which is stabilizing the object and being robust to perturbation. So there is a part which is physics related, and there is a part which is cultural. So this is what makes the problem challenging and interesting. And again, there's a huge set of techniques on how to, infer good grasping strategies and combination of learning, simulation, and classic robotic stuff that I won't get into, but I want to just expose you to the fact that this is an interesting problem. And then we, learn here. So these are all examples from this paper from Saurabh Gupta's group. Okay. There is this other trick which is a precursor to using the video for training a robot, which is that you have a human interacting with some objects in the environment, and then later on you want to have the robot interact with the same objects. And they use this training for opening various kinds of cabinet doors. And they did a real field experiment where you go to different offices and kitchens and so on, and you open cabinet doors. So the problem is the following, that if you want to use raw image data for training, then you're going to try to say, I want to copy this sequence of images, right? So the robot is going to try to move the robot hand in a way such that you get that sequence of images. But the data is messed up because the data has a human manipulating the object. So it has a human hand. And there's nothing that the robot can do to make its hand look like a human hand. So therefore, what you need to do is to solve a factorization problem. The factorization problem is you have this video, this on the left. Oops, sorry. What's happened here? So you see this picture with this person's hand on that plate with some salad or something, right? Now, what we want to do is to factorize and remove the human hand from the figure and have some kind of in-painting which completes what the scene would look like without the human. So then the robot can use that as the training signal for the trajectories. So these are examples. So one is some kind of kitchen example. Another one is some kind of a opening cabinets example. And how do they do it? You can, computer vision techniques. You can make use of the temporal history in some way. And so what they've got is the scene with the objects of interest and the human. And then you separate it out into the hand of the human. And then what's the environment minus the hands. So the robot's role is to deal with the second figure, the sequence of manipulations the changes that happen in the environment. Okay, and so you're segmenting out the hands from the.
Old school, right?
Yeah.
I mean,
Well, old school done with new techniques. So of course there's a diffusion model in here somewhere. Okay, so there is a video in painting diffusion model, and it makes use of the temporal history, and there's some cross attention, and you can read this if you're interested. But my point was, we use computer vision machinery to solve problems like this. I mean, this is not difficult for a computer vision person to think of how to solve this problem. And then you can create these kinds of missing. Now the hand is missing, so now the robot basically has to try to copy the sequence of transformations of the in the environment. Okay, so sometimes the hand doesn't completely disappear, but it mostly seems to do a decent job. Okay, so the left is the real video, and then the right is the video minus the human hand. Okay, so now this is minus the robot hand in this case. Okay, let me. Okay, so this is the use of. Yeah, so this is essentially working at a higher level of abstraction. You are working at the level of affordances, and in this case, what you are doing is a reward function. So this goes back to the dense reward idea that I talked about in the first lecture. The sequence of poses, you try to copy each pose. So in this case, it's not done in the 3D space, but 2D space. And they really use this and to solve the problem of opening drawers. So the claim is at UI you see their robots not to open drawers. Okay. So now, of course, this is a popular task in many of these systems, but I think what Saurabh's group did was is the way I think testing should be done. Is that they did the equivalent of my Airbnb test for navigation. So you go to some place you haven't been before, you take your robot, you put it down, and it has to open the drawers. As opposed to very often in the kind of teleop data that has been collected and then used in behavior cloning, very often there are subtle ways in which you are overfitted to the tabletop where you have collected the data. I mean, testing properly. I'm just saying good science. Good science means good experimentation. Good experimentation means that you need to, when you do your testing, you should not have any, contamination from the training set. So you just go. You have to. If your robot can open drawers, you should go to your grandmother's house and have it open drawers. If it can't do it, that means it should not only work on the 8th floor of Berkeley Way West, right? I mean, we can collect data there and we can make it work, but it needs to work in general. If you're going to sell a home robot for millions of people, it has to work in millions of homes.
That's true, but it feels like the field kind of took a different approach, just fine-tune everything. So, like LLMs, right? Just find and train on everything. And then
yeah, well, I now my belief is that I mean, I don't think you'll sell many robots if the robot has to be fine-tuned for many days to get anything real, right? I mean, whenever you have to do a lot of work yourself to set up things, like the old joke used to be, I mean, you guys are all young, so you don't know this. People used to have VCRs, which they used to record TV shows. And the old joke was nobody knew how to program their VCR to record the TV shows. So every VCR would have some flashing number, which was that time because the owner couldn't figure out how to use it to record a TV show. So if your robots are going to be like that, you're not going to invest $10,000 or $20,000 in a robot. It has to work. when you buy a dishwasher, it works. It doesn't have to be fine-tuned for your kitchen and your plates, right? So, okay, and then we have some. They have some experiments which show that it learns faster this way. Okay, let me. I have some slides which are from. Okay, let's see. Do I have the slide in the wrong order? Yeah. So here's a paper from Deepak Pathak's group, which I liked, which is on affordances. This is another one of these affordance papers. So there's a whole family of papers from the computer vision community which are on affordances. And they basically amount to find the hot spot from where humans are interacting with it, and then the local trajectory, which is what's the direction in which the object should move. And here they capture it by with the help of some kind of a vector which indicates the direction of movement. So that's what you abstract from the human videos, and then the robot tries to do this. So what I like about this paper is you can, I don't think I'm going to click on it now because we're going to run out of time, is that they actually, they show that you can, I mean, have real robots which can make use of these affordances. So this is a nice paper. And how does it work? It works with the top, the left part is learning visual affordances and deployment on robot. So that high-level structure that I talked about in my previous lecture, which is you want affordances and then you want subroutines. Okay, I think that decomposition still makes sense. So affordances is where on the object, and then what do you do afterwards, which is some kind of a trajectory of the object's movement. Because the morphology of the human hand and the robot hand are different. So the abstraction has to be, how does the object move, right? So that's what they have here. They've got some encoder, trajectory network, contact point, heat map, trajectory. Okay, so that's the left part is what you do at training time, and then the right part is how you deploy in a robot, and they managed to make it work on real robots. Okay, this is the okay. Should I try to click this? Let me see if it works. No. Okay, I have. So let me use the remaining 10 minutes to show some work from Himanshu, who's here on. It's all in this family of reconstructing 4D hand-object interactions. Oh, the music. We shouldn't have music. Okay. So these are what kinds of reconstruction we can do. Okay. Again, these are good examples. As I said, the problem is hard. Okay. So this is an example of an effort in this prediction. And here you're actually trying to learn from the trajectories. So what that means is that you have to deal with the retargeting problem. So the retargeting problem is that the human hand is different from the robot hand. So you have to find some way to get some conversion. And okay, so you have a video data set, you have 3D hand object trajectories, and now you convert it to a robot data set. So you are trying to transfer the human pose into a robot pose. And now you have to get the right movement, so you can use inverse kinematics for that right movement. So now you've got a whole bunch of trajectories, right? And then these go into this again. So the transformer, causal transformer idea where you are doing next token prediction, we've already seen that before. So this is a general trick which is going to work. And then you okay, let's see. So these are now just some demos. So the final part is, if you will, fine-tuned using teleop PC kind of stuff, but on top of this representation which has been trained on video. And if you don't do that, if you have a relatively small number of demonstrations, then the diffusion policy is not so good. You see the shaky trajectory, and you get the benefit of this video experience through this pre-training stage. So this is one demo. Here's another one. Himanshu, do you want to add any explanation or?
The numbers for diffusion powers are actually very low, but to get demos, we ran everything 3 times and took the best ones.
I see.
This is not description of the numbers.
Okay. Okay. Yeah, this is not speeded up, right? Yeah. Okay.
The advantage here is the transformer or the video representation over the diffusion policy.
So yeah, they didn't get what you said.
The advantage here comes from the transformer or from the video representation, because the comparison is with the diffusion policy.
Yeah, so the diffusion is trained only on video data, but our policy is trained with all the videos and then add a little bit of downstream.
Okay. Let's see. I can show you one more a paper. There's a line of papers from Deepak's group and also from Deepak's group at CMU and Laurel Pinto's group at NYU, and which are all in this mode of, okay, trying to get some robot policy with some learning from humans. But very often what is done is that the human demonstration, which is being copied, is in the lab. And in my mind, that's not pure visual imitation learning. I want to be able to get, demos, examples in the wild. The people whose videos are on YouTube, they did not do their task thinking that somebody was going to do a robot imitation. So that to me is the genuine version of the problem. But I think we are a ways there from success on that. So I could show those videos, but there's a nice work from these groups, but I think it falls short of this grand goal of learning from raw YouTube videos. But with that, let's throw the floor for questions, discussion. We have, I think, 5-7 minutes, which I think we can use for discussion. Yeah.
And driving,
That's what Tesla is trying, right? So in theory, I mean, Tesla has data. I mean, I don't know what Tesla is exactly doing, but theoretically they have data on what cameras are collecting and what drivers are doing with respect to the steering and acceleration and so on. So certainly, the earliest examples. So wait. No, this is not visual imitation. This is essentially just this is closer to behavior cloning. In fact, the earliest example of policy learning like this goes back to 1988 or 89. In CMU, they tried to train their vehicle at that time to drive. And the way they did that was that they collected images at low resolution, like 32 by 32 pixels, and then the driver commands. So they just recorded that. And then they use that for the neural network. So this is, I mean, we're talking about like 1990, right? How many years ago? That's like 30 years ago. And then there have been versions of that done multiple times. So there's work done at NVIDIA where they have a front-facing camera and then cameras facing slightly off. And then the front-facing camera gives you the correct input, and the side-facing, not side, but like 30 degrees off cameras. Those are used to essentially provide signal for when you go slightly off, how do you correct? But that, I would call that as falling in the behavior cloning paradigm, not in visual imitation. Which, yeah. So fleet learning is, yeah.
We talked about before, just saying that like it's best to have your test environment separate. I get like looking into like your robotics in the past to see a lot of things like a room builds in like 2 hours, like mapping out your environment. I guess like why isn't there more of a prevalence of like I'll say like this test time training? Like I feel like there's a lot of papers where you'll do like what you're talking about where you do behavior cloning and then you like train the simulator and you deploy the environment. There's an argument about like in context system ID, but there's not a lot of work where you actually like train as you go around.
Yeah, no, I mean, test time training is totally fine. I mean, in the sense that like the examples that I have for navigation, you take your mobile robot and you put it down and then you say, go to a TV. Okay, it doesn't know the apartment. So what's it going to do? It's got to explore, to build a map, to find the TV. So that is okay. You expect a robot to have to explore to build something. So, but it should be a robust procedure. It's not that I'm trying to fine tune it to solve some basic capability which should just be there. It should learn about, a robot has to come to your home and know the map, learn the map of your home. I mean, if you employed a butler or whatever, if you imagine that you are some rich English lord and you have a castle and you employed a new various staff like upstairs and downstairs kind of situation, they would have to acquire the knowledge about your particular place. So that's totally okay.
I guess rather than like doing a SAM-like approach where you map out the environment and use it as like I'll call it a world model to navigate around. I mean more of an approach where you directly like fine-tune the neural network and become simplistic, kind of like maybe like human brains and buildings.
Yeah, no, some fine-tuning is okay. We always become good at tasks with practice. So that is okay, but you have to be able to do a reasonable job in the first instance. Yeah. I mean, I shouldn't have to train you to use my knives. If you go to a friend's house and you're helping them cook dinner and they say, okay, can you chop the onions? You don't say, okay, give me a 5-minute tutorial on how to use your knives, right? So we always, I don't know, suppose you rent a bike and there's a different bike from the one that you have ridden before. You're going to do like a few seconds of adaptation before you get used to the controls and the compliance of that bike. That's totally okay. It's just that when more is required, that essentially implies that you didn't really solve the problem. More questions? Comments? Okay, we can end. Thank you.